Okay, good morning, everybody. Today we're going to talk about something called index theory. And I know the topics of the lectures are a little bit funny sounding, right? Index theory, right? But the idea is, once again, to try and understand dynamical systems and what they can do, right? And this is a typical phase diagram of a dynamical system. In this case, it has three steady states, right? And two of them are called what? What's this called again? What type of steady state? Abdon. It's a stable node, right? Let me just call it a node. A stable node, sure. This guy is called a saddle. And this one is also a node. All right. Notice, you might have noticed this kind of behavior. You have two nodes and you have one saddle in between, right? So you can ask yourself the question, is there a dynamical system that, let's say, only has nodes, for example, or only saddles without any nodes? Do they always have to come in groups like that, right? Why is it that it seems to be two nodes in one saddle, for example? So in general, question. Can you have, or can a dynamical system have only nodes and no saddles? Or only saddles and no nodes? Or only stable spirals and no saddles? Things like that, right? You can ask a lot of questions of this type. So what can you have and what can you not have? And here, the following is a very simple, I mean, the theory is a little harder to write in detail, but the idea is very simple. It's a very simple way to narrow down what can happen in dynamical systems. So suppose that you have a dynamical system, y prime equals f of y, and you have closed path C. So what do I mean by this? I have some dynamical system. I have arrows pointing every which way. And what I do is I define a path. Something like this, a closed path, and I call that C. Mind you, C does not have to be a periodic solution. It may look like a periodic solution, maybe, but it doesn't have to be. For example, in this case, it's not a periodic solution at all, right? Just a closed path. What are we going to do about the path? Okay, so the index associated to C is the number. I'm going to write it down and it's going to look a little funny, but I'll mention graphically what it means. It's the number of counterclockwise rotations of the vector field as you follow C counterclockwise. Okay, it's really much better to write it to say it down and to say it instead of writing it down. So what you do is, let's say that my marker is an arrow. Okay, this is the tip of the arrow, so it's pointing this way. What I do is I stand somewhere on the path, and I start walking back counterclockwise along the path. And I'm always pointing in the direction of the vector field. So if the arrows move that way, I move that way. If the arrows move that way, I move that way. And if I end up turning around, okay, then I count how many counterclockwise rotations I do with the marker until I get back to where I started. Okay? It has to be an even number, an integer number, right? You can't, because we ended up where we started, we ended up pointing in the same direction we started. So the number of rotations is an integer, right? If it rotates counterclockwise 3 times, we say that the index is 3. If it rotates clockwise 3 times, we say the index is -3. That's right, -3. Let's do a few examples of this. It's actually very simple. All right, so for example, stable nodes. So I'm going to give you an example of a stable node and a dynamical system that looks like this. Of course, it's pointing inwards like this, right? I'm going to draw my my path to go around the stable node. And now let's look what happens with my marker, right? I'm going to start here. Okay, ready? I'm going to start moving counterclockwise. Imagine that you're always pointing in the direction of the vector field. Now I'm pointing over here. Now I'm pointing like this. Now I'm pointing like this. And now like this. Okay, so how many counterclockwise rotations did we do? Did you count? Oh, come on. Let me do it again. Ready? Like this, like that, then like this. 1, right? Okay. And that one was counterclockwise or was it clockwise? The one rotation was counterclockwise, right? So the index is equal to 1. Okay? Let's do another one. Saddle. So suppose that I have a point here and it looks like a saddle. Of course, this is pointing inwards, right? And this is pointing outwards. And I have my my closed path over here. All right, so I'm going to start, let's say I'm start over here, okay? So I start moving around. The vectors over here are pointing that way, so I'm going to do this, okay? And they're pointing that way, so I'm going to do this. Okay, and then they point over there, so I'm going to do this. And then down here. How many turns?
1 turn.
1 turn. Was it clockwise or counterclockwise?
Clockwise.
It was clockwise, right? Did everybody see that? I'm going to do it again. A little faster, okay? Like this. Okay? So the index is -1. That's right. Let me do another example. Periodic solution. So now we're going to have, I just said you should not confuse this path with a periodic solution because they're different, right? But in principle, it could happen that you have a periodic solution. So you have a vector field that is always pointing, let's say, in this direction, right? And I don't have to, but I can take the path to be just the same as the periodic solution. So my path C is the same as the periodic solution. Okay, what do you think is going to be the index? All right, let's just do it. Okay, we're going to start here on top, right? I'm going to go counterclockwise, and I go like this, right? So how many times did I turn?
1.
Counterclockwise or clockwise? Counterclockwise. So the index is what?
1.
The index is 1. Okay, so you're saying, well, but that's kind of cheating because the periodic solution was going this way. What if the periodic solution was going the other way? So what if the periodic solution was going like this? In other words, clockwise. What do you think the index is going to be, Abdon? Well, or actually Daniel? So before we just did the periodic solution that goes counterclockwise. Now we're going to do the periodic solution that goes clockwise. -1, okay. Actually, I would have thought -1 too, but let's see what happens. When we do the path, okay, mind you, the fact that the periodic solution goes clockwise doesn't change our path at all, and it does not change the definition of the index. The index has to go the number of counterclockwise rotations as you move along counterclockwise, right? So even though the periodic solution goes clockwise, I still have to do it counterclockwise, right? That's what the definition says. Okay, let's do it. So now I'm going to start, let's say, here, and I'm pointing that way, right? Because that's where the direction is flowing. Okay, and I go like this, like this. What was that? Counterclockwise, right? How many times? 1. So the index is still equal to 1. Okay? All right, so now we have something that seems now much, we have some kind of theory already, what's going on. The nodes have index 1. By the way, what do you think about an unstable node? Let me just write it here. Example, unstable node. Unstable nodes point outwards. Okay, and if we do the index of that, we get what? So start here, go around. 1, right? Great. So we have 1 for unstable nodes, we have 1 for stable nodes, we have 1 for actually spiral in, spiral out, you can draw it, same thing. We have 1 for periodic solutions going either way. We only have -1 for saddles. Okay? All right, that's something we should remember. Everything seems to be 1 except for saddles that have value -1. Now let me write down a lemma. Okay, I'm going to first tell you what, I'm going to first draw the diagram and then we can see what the lemma looks like, okay? So suppose that I have a vector field, once again, y prime equals f of y. I got a bunch of arrows pointing every which way, and I got an arbitrary path, okay? And suppose that inside of this region, I got a bunch of steady states. For example, this one, this one, this one. Okay? And I want to find out the index of this path. Now here's what I'm going to do. There's no more steady states, only these 3, okay? Inside of this thing. What I'm going to do is I'm going to deform this red path in here. I'm going to consider a different path. I'm going to consider the following path. One that goes around like this, then goes like this. It goes around, like this. All right, do you guys agree with me that the index of this path is the same as the index of this path? Well, there are no steady states in here. As long as there's no steady states on the way, the direction of the arrows is not going to change very much. It's going to maybe wiggle around a little bit, but it's not going to change dramatically, right? So actually the index of this guy is equal to the index of the guy inside, right? And go around, whatever. And this guy is going to do something very similar, okay? Moreover, this path, this length of path over here is very much going to undo this length of path over here. For example, if I go around counterclockwise this way, I'm going to go back clockwise this way. So these two are going to cancel each other out, right? So basically, if I want to compute the index of this large path, what I should do is I should compute these 3 indices, and then what? And then add them up. Exactly, right? So there you go. So if I want to compute the index of a big path, I look at all the steady states inside, and I look at the local, index around that path. So define I of, I don't know, x to be the index around a steady state x of the system. Okay, and now I can actually write the lemma. Let me write the lemma over here. You got a vector field in the dynamical system y prime equals f of y, and C is a closed path. Then the index of that path, the index of C if you will, is equal to the sum over all steady states that lie inside C of the index of X. Okay, so once again, maybe the formula looks a little bit funny, but that's really what it means is this. You take every one of these indexes around the steady state and you add them up. Questions? What do you think, Krista?
Sounds easy.
Sounds easy? Okay, good. It is easy. So, right. But then we can draw a bunch of conclusions from this. Just from what we did. For instance, suppose that we have a periodic solution like this. Okay? The index is equal to 1. We've seen it, we've calculated the index. We know that it's equal to 1. On the other hand, it's equal to the sum of this thing, right? So is it possible that a periodic solution doesn't have any steady state inside? What would happen if there was no steady states inside this periodic solution? The index would be what? 0. Would be 0, right? Because there would be nothing to add on the right-hand side. So that means that every time you have a periodic solution, there must be something inside, a steady state inside. Right? Well, that's a powerful result. We didn't know that. That's kind of surprising already, right? Whenever you have a periodic solution, there has to be something lying inside. Okay? Now, could that something be a saddle? It can't be a saddle because saddle has index -1. If there was only a saddle in here, that means that the index would be, this right-hand side would be -1, this left-hand side would be 1, you would have a contradiction, right? So what if we know that there's a saddle in here? There has to be at least 2 other steady states. That's right, you got it. And they cannot be saddles, right? If they're saddles, then there have to be even more, right? So basically, you have to have this thing add up, right? That's the idea, okay? So every periodic solution must contain at least one steady state okay. Actually, let me say one more thing. Bounded systems. Okay, so suppose that a dynamical system is bounded in the sense that solutions don't blow up to infinity. Okay, so you can imagine a dynamical system that is bounded as ultimately pointing towards the inside of some region, right? No matter where you start, you kind of have to stay within some region, right? And therefore, there has to be a large enough region where you can do this. There has to be a large enough path C where all the arrows are pointing inside. And if all the arrows are pointing to the inside, then what's the index? The index is 1, right? Let me do it. It's basically the same thing as a stable node, right? You start here, you go around, index is -1. Sorry, 1. Okay, so bounded systems must have at least what? One steady state, right? Otherwise the index could never be 1. Must have at least one steady state. Okay. Now, what happens when there's a saddle in a bounded system? If a bounded system has a saddle, then it must have what? Okay. If a bounded system has a saddle, then it must have 2 more steady states. So that's it. That's the formula. You basically, whatever you do has to add up. The right-hand side has to add up with the left-hand side. It's a powerful formula that allows you to conclude a lot of things about what can happen and what cannot happen. Good. Now let me give you a concrete example of this. A more concrete example of this theory, which is called index theory. And I'm going to go back to what we've talked about for some time already before, which is periodic solutions. You want to prove things about periodic solutions. In this case, we're going to prove that a periodic solution does not exist. How's that? That's pretty cool, right? If we can prove using this index theory that a periodic solution cannot exist, that's powerful information, right? I mean, you guys know it's hard to prove these things, right? So we prove that the following system has no periodic solutions. Okay, what system is it? I'm going to write it down. It's x prime equals 2x times 4 minus y minus x. Y prime is equal to y times 5 minus 2x minus y. So just to clarify, because my 4's and my y's apparently are similar, this is a y, this is a y, and that's a 4. Okay, that's a y too. All right, this system is actually a special case of a Lotka-Volterra competition model. We've already talked about them, we've already described them, and we informally showed what the dynamics looks like, but we were not completely 100% precise. We basically just described it a little bit hand-wavy. So now we're going to prove in a completely rigorous way that there cannot be periodic solutions for this system. Okay, so how are we going to do this? Well, first of all, which steady states does the system have? Okay, so in principle what you can do is you can set this thing equal to 0 and you solve for the steady states. Now, we actually know what happens with the system in particular cases. For example, if we set y equal to 0, okay, we have the system x prime equals 2x times 4 minus x. Does anybody remember what this kind of system this is? When we set y equal to 0?
Logistic.
It goes back all the way to the beginning of the quarter. It's a logistic system, right? So if y is equal to 0, system reduces to logistic model x prime equals 2x times 4 minus x, and similarly for y. Okay, now what are the steady states for this system, for this reduced system? Well, 0, I'm sorry, this is an x. Yeah, 4 minus x. 0 and what else? 4, right? Okay, good. Do it over here. Okay, what about, all right, let's just draw a phase diagram of this thing. Okay, so now, if y is equal to 0, that means there's no, I don't know, rabbits or whatever, there's only sheep. And the steady state can be either 0 or 4. Okay? That's when y is equal to 0. There can be two steady states. So we know these are actual steady states of the system, even of the two-dimensional system, right? If you set y equal to 0 and x equals 4 or x equals 0, you have a steady state. Okay. Now, we also know what the dynamics of the system looks like when y is equal to 0, when there's no rabbits, there's only sheep. Do you guys remember what the dynamics looks like? Over here, you can converge towards 4, and over here, you converge towards 4, right? If you start here, you stay there. If you start with a slight small number of sheep, then it's going to converge towards 4. Right? If you start with more, you converge back towards 4. All right. The same thing for over this dimension over here. If we have no, whichever of the other animals, what did I say, sheep? Okay, so if you have no sheep and you only have rabbits, right? Then dynamics is also like that. Goes up and down. And in this case, if we have no x and we only have y, then we converge towards y prime equals 5 minus y. Sorry, y times 5 minus y. So the other steady state is right here at 5, right? You go up, you go down. Okay, and there is one more steady state. Actually, we've already found 3 steady states, 1, 2, 3. The other steady state is the one where there's x and y are both bigger than 0, and you can just set it equal to set the right-hand sides, set those things equal to 0 and find them. And the steady state is actually equal to 1,3. Okay, so you can just set the right-hand side equal to 0. We can actually do it analytically. That's not a big deal. But you find that steady state is 1,3. All right, so now what? How do we find out what kind of system these are? For example, if I wanted to determine if it's a saddle node or a saddle or a stable node or a spiral, we can linearize, right? Okay? We can linearize around each of these steady states. But we're not going to linearize around most of them. We're only going to linearize around this one for a reason that I'm going to mention in a moment. Notice that if a solution starts, say, over here, it's never going to get out of this axis, right? It's always going to stay in the axis. If it starts over here, it's always going to stay in the axis. can this state be part of a periodic solution? What do you think? Could there be a periodic solution that crosses this axis, for example, that goes around like this? Why not? Brian. So question, right? So the question is, can you have a periodic solution that, say, starts over here and then comes back?
Well, isn't the arrow will be pointing up? So
That's right? The arrows are pointing up. So if you ever got to this point, you would just converge towards 5. That's it, right? So you would never actually have a periodic solution. So that means that periodic solutions cannot actually cross the x-axis. Sorry, the y-axis. Can it cross the x-axis? No, right? For the same reason. Okay, so periodic solutions could never cross the x-axis or the y-axis. Okay, do you guys agree? Awesome. Now, we said that periodic solutions must contain at least one steady state, right? We already showed this. So, what steady state could it be? Can it contain this guy?
no.
This guy? No, right? Because if it was any of these three, it would have to cross the x-axis or the y-axis, right? So it has to contain 1, 3. For example, you can think about a periodic solution that was always lying over here, down here. That periodic solution would have no steady states inside it, so you cannot have one over here. It has to contain 1, 3, right? Let me write this down. On the other hand, periodic solution, a periodic solution would have to contain a steady state. Okay? Therefore, the only steady state you can possibly contain that is not on the axis is the steady state 1, 3. Therefore, any periodic solution must contain the point 1, 3. So it must look something like this. Well, actually, I should draw this with black. Sorry, with blue, because it's not a path. It's a periodic solution. Okay. All right. But what prediction are we making in case that there was a periodic solution? What can we say about 1, 3? It cannot be a saddle because it must have index equal to 1, right? All right, let's write it down. Okay, since the index of the periodic solution is equal to 1, the index of the steady state 1, 3 must also be equal to 1. Now, do you think that's going to be true or not? Okay, let's calculate the Jacobian around this steady state. We'll find out whether that steady state is a saddle or not. So the Jacobian is, let's see, so this is 2x times 4, 2x minus y, 2x times minus x. So what would be the Jacobian in general? Who wants to try? Natalie? So 2x times 4 is 8x.
So 8
Uh-huh.
minus 2y, and then minus 4x. And then the next one would just be negative 8x. I mean, no, negative 2x.
Yes, negative 2x. That's it, right?
Yeah, for that.
Daniel, do you want to try the next one? So we're derivating this function with respect to x. Almost. Minus, right? Okay. And what about derivating this function with respect to y? Minus 2x
Plus 2y.
minus, right?
Yeah,
Minus
minus 2.
2y. Okay. Now let's evaluate that at the point 1, 3. Okay, so we got 8 minus 6 minus 4 is minus 2, I guess. Right? 6 minus 4. Okay, this is minus 2. Minus 2y, and y is 3, it's minus 6. And 5 minus 2 minus 6 is minus 2. No, minus 3. Okay, so this is 5 minus 2 minus 6. And this guy here is 8 minus 6 minus 4. Okay. All right. So now what? What is that? Is that a saddle? Is that a stable node? What is it? Well, what is the determinant? Let's say we call this A. The determinant of A is 6 minus 12 is equal to minus 6. In fact, just knowing that the determinant is negative is already enough to show that it's a saddle. You can actually compute the whole thing, but and maybe I should dwell a little bit more on this next time. But if you remember, if you set this equal to the determinant of A and this equal to the trace of A, the eigenvalues can be written as minus this plus or minus tau squared divided by 4 minus the determinant, okay? But the determinant is negative, so this is a plus something, right? So that means that this number here is real and is bigger than this. So you can subtract it or add it, and you get a positive eigenvalue and a negative eigenvalue, right? So bottom line is that this thing is a saddle. Or you can also do a more thorough analysis where you simply, find the eigenvalues of this matrix. Either way, we conclude that 1, 3 is a saddle. Okay. So then we put all together. We said that if there was a periodic solution, that periodic solution would have to go around 1, 3 and nobody else, right? But 1, 3 is a saddle. So the index the index of the path C is equal to -1, basically it's equal to the index of the point 1, 3, which is equal to -1. And that is a contradiction, right? Which is a contradiction. So we can conclude that there was no periodic solution to begin with, right? So there cannot be a periodic solution in this system. Okay? Awesome. Do you guys have any questions? What about, I mean, this is all in 2 dimensions, right? Would this work in multiple dimensions, like higher dimensions?
You'd have to take like a sphere or something.
Yeah, you'd have to take a sphere.
Or something.
What's counterclockwise then?
What does counterclockwise mean exactly? How do you go around with a marker around the whole sphere, right? What does that mean, right? So it turns out the whole marker thing does not work anymore. You cannot think about it as marker. But there is a theory that is also very simple. You know, you can also do it very intuitively. That that allows you to compute the index of a steady state. It involves looking at finding the eigenvalues around the steady state. For example, let's say the index around just one steady state. Okay, not a path, because what does even path mean in this case, right? Right. So you take the eigenvalues and you look at the signs, and you can tell from calculation of the signs, you can calculate the index around each steady state. Okay, and then you can carry out similar arguments, and it generalizes nicely, but it's different. Okay, we don't have much. We wouldn't have time to cover it thoroughly, but it can be generalized to higher dimensions. Okay, what else? Yes.
What about a spiral?
What about spirals? Let's look at the index of a spiral. Okay, so here's your spiral. And I'm going to look at a path that somehow points in the direction of the spiral. Now I have to a path that goes around the spiral. So I'm going to have to be a little careful, right? I mean, these arrows are pointing down. Okay, so you can have an idea what the vector field is pointing in that direction, right? Okay, so now I'm going to go around with my marker. Let's say we start, here, and it's pointing this way, right? More or less. So I go down, go this way, and come back. So what was the index? The index is equal to 1. And if the spiral was spiraling in this other direction, okay, then what do you think? Well, in that case, we have to point, let's say we start here, right? It's pointing that way, right? Now, it's tempting to start going this way following the flow. But remember, the definition calls for going counterclockwise, no matter what the flow is doing, right? So we start going counterclockwise, and I'm pointing always along the flow, more or less like this. And I go back here. What is that? Also 1, right? Okay. Which is actually, it's good that we did that, because what if it had been -1? It would mess up our whole calculation, right? So, or it might mess up our whole calculation. So basically, these guys all behave the same. The only guys that are actually different are saddles. Everything else has an index of 1. Okay? If we had done this with unstable spirals instead of stable spirals, pretty much the same thing. The arrows are pointing slightly differently, but they point very much the same way, and it's all the same story, okay? Thanks for asking. Any other questions? Well, what about if there is a steady state along the line of the path? What if I look at paths that somehow end up touching a steady state? At that steady state, the vector field has value 0, right? So my marker doesn't have anywhere to point. If the vector is equal to 0, you can't be pointing anywhere, right? So then what? So I didn't say this, but we actually rule out paths that go through any steady state. Okay? So paths cannot touch steady states because otherwise we have that problem. Okay? Anything else? So just to summarize, could you have a dynamical system that has 3 saddles, two stable spirals, and 1 unstable node? So could you have a bounded dynamical system that has these properties? What do you think? Okay, 3 saddles, spirals, and 1 unstable node. You could not have it because what? Because the total index is 0, right? And because we have a bounded solution, a bounded dynamical system, then the index must be 1. That's right. Yeah, you got it. That's it. Similarly, if you have a periodic solution, even for a system that has unbounded solutions, inside that periodic solution, there's only so much that can happen. Could you have one of these situations? No, because the index of the periodic solution itself is 1, and it must be equal to the sum of these things, which is 0, right? So that's it. This is actually topological arguments. This is part of basically topology theory applied to dynamical systems. Awesome. Okay, we'll stop here then.